Welcome again to Chapter 18. In this part, we're going to look at the electric force. So in the previous parts, we've seen how charges attract and charges can repel. The goal of this section or this part is to look at how big is that attraction or repulsion. What we have is we have two charges, potentially, maybe more, that are some distance apart. So let's say I have a positive charge here and I have a positive charge there. If I look at the line between them, I know that they will repel each other along this line. So if this is charge 1 and that is charge 2, then this would be F21 and that would be F12. And hopefully you remember from first semester that that's hallmark of it being a third law force pair. So we expect that these two forces should be equal and opposite. The law that governs the force between two charges is Coulomb's law. The magnitude of the force between two charges, so F12, is given by a constant, K, multiplied by Q1, multiplied by Q2, and divided by R squared. Now, if we go back a slide, Q1 and 2, well, this would be Q1 because I labeled it 1 here. This would be Q2. R, you're thinking radius, which is not bad, but in this case R is more general, and what it is it's the distance between the two charges. Okay. K has a value of 9 times 10 to the 9th Newton meters squared per Coulomb squared. Now, you've seen a force very similar to this in the past if you took Physics 201 with me. And that is the gravitational force between any two massive bodies. Remember, that was a constant G multiplied by the two masses divided by the distance between them squared. So there's a lot of parallels with how the electric force behaves to how the gravitational force behaves because functionally they take the same form. Well, that gives us the magnitude of our two forces. And I should say here that these Q's you should absolute value because we don't want any negative signs or minus signs that come in with the charge to mess around with what we know has to be happening with the directions. So how do we determine the direction? Well, we go back to opposites attract and likes repel. So let me give you an example of why we would want to absolute value really quick. Let's say I have a -1 Coulomb charge here and a +2 Coulomb charge. The force from the 2 Coulomb on the -1 will be towards the 2 Coulomb. And the force from the -1 Coulomb on the 2 Coulomb will be towards the -1. If we look at the magnitudes and we don't absolute value, I forgot the C, times 2 Coulomb, divided by the distance between them squared, which I'm just going to leave as R. F -12 is this. F2 -1 is going to be the exact same number, as we know it should be because these are a third law force pair. But one of them is going to point in the positive direction, and the other one will point in the negative direction, depending on the coordinate system that we have set up for this problem. Therefore, I don't want that negative sign that comes in with that -1 Coulomb to stick around because I'm going to put the negative sign in when I actually assign the directions to these forces. I hope that helps. Opposites attract, likes repel. We're going to do a bunch of examples where, well, you'll see how this works. Okay, so a 1 Coulomb charge is 3 centimeters from a negative Coulomb charge. For Coulomb's law, does it matter which one I call Q1 and which one I call Q2? If you think about the formula, F equals K times Q1 times Q2, notice the nice absolute values there, over R squared, and I use small q or I use capital Q. Either way, Q is charge, almost universally. I can't think of an exception in physics off the top of my head where Q means something other than charge. Does it matter which one I call Q1, which one I call Q2? And the answer is no, it doesn't. And the reason is because of the properties of multiplication. I can take 3 times 2, and that will equal 2 times 3. I believe that is the commutative property. And multiplication is commutative. Addition is commutative, but subtraction and division are not. So, for example, 2 minus 3 does not equal 3 minus 2. So that's not the case. But it is the case for multiplication. And since Coulomb's law is multiplied, we're good to go there. How does this support Newton's third law? Equal and opposite. It means that it doesn't matter which one I call which. I'm going to get the same value out when I do my multiplication. Equal and opposite forces. We saw last semester that the gravitational force was an inverse square force. And remember, if something is an inverse square force, then the force is proportional to 1 over r squared. So the fact that it is in the denominator makes it the inverse portion, and the fact that the denominator is squared makes it the squared portion of that name. So as a reminder of how inverse square forces behave, I have a couple of examples. So 2 charges are separated by 1 meter. I don't give you what the charges are because it doesn't matter for this problem. What I do know is that the force between those 2 charges is going to look like this. F equals K times those 2 Q's divided by 1 meter squared. And I'm going to give this a subscript of O for original. That's not a 0. It's an O for original. Okay. Now what I'm going to do is I'm going to move these 2 charges so that they're only half a meter apart. So what happens to the force? How does it compare to the original one? So the charges didn't change. So K, Q1, Q2 stays the same. But my denominator did. And now it's 1/2 meter squared. Well, 1/2 squared is 1/4. So I'm going to put that in. Okay. And now I need to reconcile this improper fraction. And remember, to reconcile an improper fraction, you invert and multiply. So the 4 cancels the 4, the 1 cancels the 1. The units need to stay either there or with the 1, however you want to think about it. But what I end up with is a factor of 4 times K times Q1 times Q2 over 1 meter squared. Well, if you look, a little bit too far over. Let me try again on that. Actually, let me just change color. If I look at, hopefully you guys can see the yellow, this much of it, that is exactly this. It's a little hard to see. So I'm going to switch back to red, which means I can write F nu as a factor of 4 times the original force that I had. So by changing the distance or decreasing the distance by a factor of 2, it went from 1 to 1/2. The force increased. I decreased the distance, the force increased. So there's that inverse coming in again. but not by a factor of 2, instead by a factor of 4, because it's an inverse square force. I can do the same thing, but instead of moving them closer together, I'm going to move them further apart. So my original force is exactly what I had on the last slide. 1 meter squared. And my new force is going to be K times Q1, Q2 over 3 meters squared. Okay, well, 3 squared is a factor of a 9. So that's 1/9. And now I'm going to separate this out, so I don't have to switch to yellow again, because it was really hard to see. Notice 9 times 1 is 9, so that's an okay thing to do. And then this portion here that I pulled off to the side is exactly that up there, which means that F nu is now 1/9 of my original force. So the distance increased and the force decreased, and again you can see that that square popped up. In the next part, we are going to be focusing more on numerical examples involving charges and Coulomb's law, and actually doing calculations.